Okay, so we're going to start talking about Chapter 6. So Chapter 6 is again going to kind of deal with a little bit different of a topic than what we've been talking about recently. Okay, so as you guys remember, hopefully, in Chapter 2, we had kind of dealt with how we knew what matter and what atoms consisted of. So we had talked about the various subatomic particles of matter. And so where we had kind of left that discussion is we had found out that there was a nucleus, right? And in the nucleus we had both protons as well as neutrons, right? And so protons were our positively charged particle. They also contributed mass to our atoms, and the neutrons were neutral, right? They didn't have any type of charge, but they also contributed mass to our atoms, right? And both of these guys were located in the nucleus. And so then we also knew that there was another particle out there, another subatomic particle, which was the electrons. And the electrons gave us our negative charge, right? So that essentially all matter was electrically neutral. We had an equal number of protons as we did electrons. The other thing about electrons, though, was they essentially had no mass. And it's kind of not correct necessarily to say that they have no mass, but their mass was so small comparatively to the protons and the neutrons that they essentially didn't contribute any mass to the overall atom. Okay, so electrons do have mass, but it is incredibly, incredibly small. All right, so this chapter is going to deal with the electron. That's what we're kind of highlight and focus on in this chapter, because we'd kind of left it up in the air about what they were doing, where they were in the atoms. We are going to ideally come to somewhat of a conclusion about what electrons are doing and where they are in our atoms, and then we're going to be able to expand that further in the next few chapters in talking about bonding. Okay, so the answer that we come up with long term with what electrons are, or where they are, what they're doing in our atom, is actually going to be kind of unsatisfactory. Okay, so why would that be? So the overall theory that tells us what electrons are doing and where they are in the atom is what we call quantum mechanics. Okay, and so quantum mechanics as a theory was developed in like the early 1900s, right? And it was developed by a lot of very, very, very intelligent people, including Albert Einstein, Niels Bohr, etc. Lots of people helped contribute to the development of this theory. Okay, so up until the beginning of the 20th century, up until the beginning of the formulation of quantum mechanics as a theory, all physics and all physical phenomenon had believed to be very deterministic, right? So what does deterministic mean? So for example, if we were to think of a ball, like, so let's say some sort of baseball, right? And you were to throw that baseball into the air, we could predict with fairly certain probability where that baseball would land, right? If we knew the factors that were working on it, so the forces, the wind resistance, etc., the trajectory at which we threw it at, the velocity that it was going, we could predict with fairly decent certainty that it would land, let's say, 100 yards away from us, okay? Okay, so that's what we mean by deterministic. With knowing various features and various characteristics of whatever thing we're dealing with, we can kind of predict where it's going to end up. Okay, so the problem with quantum mechanics and the problem with electrons in general is the fact that, number one, electrons, again, are very small, right? And so when we go down to the very tiny world of the electron, matter behaves a lot differently than it does on what we call the macroscopic world that's around us. Okay, so the macroscopic is our big, it's our baseball, it's our basketball. The microscopic world, again, microscopic world of the electron, again, behaves very differently than our macroscopic world that we live in, right? So if we were in the tiny microscopic world of the electron and we shot it, right, or we threw it, and we could do that at a certain velocity and a certain trajectory, etc., unfortunately, we wouldn't be able to know exactly where it was going to land, and we wouldn't be able to predict exactly where it was going to land. Instead, what we'd be given is some sort of probability distribution about which we were kind of certain that it was going to land, right? So we could say maybe with 90% certainty, we think it's going to end up about right here, right? So that's what we would call indeterministic. And what we're going to be left with, indeterministic, what we're going to be left with respect to this small microscopic world of the electron, is this kind of indeterminate state of matter, right? We're not going to be able to know with exact certainty where the electron is, where it's going to be. Instead, we're going to be just kind of given an overall probability of where we think it's going to be in an atom. And so that was very disturbing to a lot of people, the fact that we could only really describe the behavior of electrons in terms of probability didn't really sit well with some people, okay? So that's what quantum mechanics essentially gives us. It gives us this very indeterminate structure of matter. The only problem is, so again, people aren't super happy with that. The problem with that is the fact that quantum mechanics is one of the most successful theories that has ever been developed in science, right? So in terms of theories and in terms of things proving theories, quantum mechanics and the quantum mechanical model of the atom is the most successful thing that has been developed. Okay, so people are unhappy the fact that we can't know necessarily where electrons are at. We can only be given probabilities. That sucks, but it's going to be how it is because again, this is a very, very, very strongly experimented on and strongly proven theory. Okay, so long term, what we're going to get out of quantum mechanics, we're going to know where atoms or where electrons are at in atoms. It's going to help us explain the structure of the periodic table and why we actually see certain chemical reactivities with respect to various elements. It's also going to explain the behavior of bonding and chemical bonding. So all matter consists of bonds for the most part. We haven't talked about bonds, but quantum mechanics is going to kind of form the basis behind how we're going to understand bonding. So before we actually start talking about quantum mechanics as a theory, we actually first have to go and talk about light. And so hopefully long term, this relationship between quantum mechanics and light will be made apparent. But we're first going to start talking about light. All right, so light, what is light? We don't really deal with light that much yet thus far in our chemical career, but light is a form of electromagnetic radiation, right? So what is electromagnetic radiation? So essentially electromagnetic radiation is composed of perpendicular oscillating electric fields, so electric fields as well as magnetic fields. Okay, so an electric field is a region of space where an electrically charged particle experiences a force, whereas a magnetic field is a region of space where a magnetized particle experiences a force. So electromagnetic radiation consists of these perpendicular oscillating electric and magnetic fields, and they're oscillating or moving in whatever direction that they are going. Okay, so light, again, is just this electromagnetic radiation. Okay, so if that is what light is, then light is essentially can be at least thought of as a wave, right? So again, it's these perpendicular oscillating fields, these waves. So we are going to right now already assume that light behaves as if it were a wave. There are a couple of different characteristics that we need to talk about with respect to waves. So one way that we can characterize a wave is via what is called the amplitude of the wave. So if we looked at our little wave over here, right, so a little wave in little figure A here, the amplitude of the wave is given as the distance from the trough to what we're going to call a node. So the zero axis here is what we call a node, and this is what we call a crest, not a trough. Okay, so again, the amplitude is given as this distance between a node and a crest, or it can be the exact same thing between a node and what we call a trough. I think that's how you spell trough. So that's one way that we can categorize a wave, is how high it is, its amplitude. Another way that we can categorize a wave is via what's called its wavelength. So the wavelength is going to be the distance that essentially a wave travels, right? So we can measure this from a crest to a crest, we can measure it from a trough to a trough, or we can measure it from a node to a node. Okay, so again, the wavelength is just the measure of distance traveled by a wave, and we would usually measure this in terms of some sort of distance or length measurement, which would be something like a meter. Okay. All right, so another way that we can categorize a wave as opposed to wavelength is something called frequency. So the idea behind frequency is that this is going to be the number of waves, or the number of complete wavelengths that pass a given point in a period of time. Okay, so what we could do to measure frequency is we could sit at this point and we can essentially measure how many full waves get through this point as they're moving in this direction in a given period of time. And so frequency is going to have units of events per time, right? And so that time is usually in S, and so this is usually given in units of S to the -1, so this is again 1 over S. This inverse S, this inverse seconds, this has an actual unit itself. This is what is called a hertz. It's given as this guy, this Hz. So if you deal with physics, you deal with frequencies a lot, you probably have heard of what a hertz is. Okay, so if you think about waves and you think about their various characteristics, so amplitude, wavelength, frequency, if we wanted to think about the energy of a wave, there are two different things that are going to go into the total energy of a wave, right? So let's say that you're out in the ocean and a wave hits you, right? The larger the wave, right? So the larger the wave, which is going to manifest itself as the amplitude. So the larger the wave, the larger the amplitude. If you think about getting hit by a big wave, the more energy you're going to have in that wave, right? So larger waves, larger amplitudes lead to more energy. So amplitude and energy are going to be directly proportional to one another. Another way we can think about energy of waves is if you get hit by a bunch of waves in very rapid succession, then they're going to have more energy as well, right? So very rapid succession waves would have a large frequency, right? And so we utilize this little Greek letter, this guy, it's called nu. We utilize this frequency to represent, or this Greek letter nu to represent frequency. So large frequency also leads to more energy, and so frequency is also going to be directly proportional to energy when it comes to waves. So energy of a wave is going to be given by its amplitude as well as its frequency. All right, so we've already talked about how light, electromagnetic radiation, is going to behave like a wave, right? So now that we have some characteristic properties of waves, how does that actually manifest itself with regards to light? So with light, the dimness and brightness of light is how we determine what the amplitude is, or this is how the amplitude kind of presents itself. So the brighter the light, the higher the amplitude. And then the dimmer the light, the lower the amplitude. And then how does frequency or wavelength, which again are going to be related to one another, how do they manifest themselves in our light? So they're going to essentially appear as different colors. So different color light have different wavelengths and different frequencies. So for example, red light has its own given wavelength, its own given frequency. Yellow light is a little bit of a smaller wavelength, a little bit larger of a frequency, and then blue light is one of the more energetic ones. It's going to have a very tiny wavelength comparatively and a very large frequency. Okay, so I've hinted at the fact that there is a relationship between frequency of light and its wavelength. So I already defined this little Greek letter. This guy is nu, and again, it's what we represent with respect to frequency. So frequency is given by this guy. This guy is lambda. This again, another Greek letter, and this is how we represent wavelength. Okay, so I just want to make sure I write out, when I write out nu and lambda, we're both talking about the same thing. Okay, so nu is representing frequency and lambda is representing wavelength. Okay, so I've mentioned these again are characteristic properties of waves, that these guys have a relationship, right? So if we think about frequency, I've already talked about its units having some sort of number of events per unit time, so something per second. So something per second, so frequency is usually in something of inverse seconds. And then wavelength, we also talked about, had units of distance, right? So meters. So if we multiply these two things together, we're going to end up with something like meters per second, which ideally you should represent, or you should notice as being some sort of speed or velocity, if you will. Okay? So the relationship between frequency and wavelength is essentially the speed of whatever wave we're looking at. And for electromagnetic radiation, this is speed. This is the speed of light. Okay, so speed of light is a constant. It is moving at a constant speed, so that speed is 3.0 times 10 to the 8th meters per second, which is very, 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 very fast. All right, and so all electromagnetic radiation moves at this exact same speed. And so we can kind of rewrite this in this little equation, right? So this is going to give us what our frequency is. This guy is going to be our speed of light, which is a constant again, 3.0 times 10 to the 8th. And this is going to be our wavelength, right? So if I know the frequency of light, I know it's light, and I know my constant speed of light, then I can calculate the wavelength of light and vice versa. So you should also note here that frequency is inversely proportional to wavelength, right? So the larger the wavelength, the smaller the frequency. The smaller the wavelength, the larger the frequency. So these guys have an inverse relationship with respect to one another. So when we think of light in general, we always think of just like visible light, the actual light that we see. But with respect to all of the various wavelengths of the electromagnetic spectrum, visible light essentially constitute a very, very, very small fraction of those wavelengths, right? So we have on this slide the entirety of the electromagnetic spectrum, right? So this goes from things like gamma rays. Gamma rays have very high frequency, very tiny, tiny wavelengths. So we start up here at very high frequencies, very small wavelengths. And then we go down after gamma rays, we go down to X-rays. So these have, again, smaller frequencies, larger wavelengths, ultraviolet, and this tiny little region in here is the visible spectrum, infrared, microwave, and radio wave, okay? Just as a reminder, there is a relationship between energy and frequency, and energy is going to be directly proportional to frequency. So the higher the frequency, the more energy these various wavelengths of light have, right? So up here at the top, we'll have the most energetic. So gamma rays are the most energetic, and then as we move down to the bottom, radio waves are the least energetic. Okay, so that kind of makes sense, right? So these guys up here, gamma rays, X-rays, UV rays, these guys all have enough energy to potentially ionize your biological molecules, which can lead to long-term bad effects, things like cancer, etc. So gamma rays we usually associate with radioactivity, and that's usually a bad thing. Gamma rays are produced by radioactive decay. Also X-rays, so we will expose ourselves to X-rays whenever we need an X-ray, but what do they do to the remainder of your body? They usually cover it with some sort of lead plate, so the remainder of your body doesn't actually get exposed to those X-rays, so we try to limit our exposure. And the same thing with ultraviolet, right? So we are exposed to ultraviolet light all the time, but we tend to try to minimize its damage by using things like sunscreen, etc., so that we long-term don't damage our biological molecules, don't get skin cancer, okay? Okay, so after these guys, so these are the most energetic, and they have enough energy that could potentially damage your biological molecules. After that, we move into visible. So visible, going from the smallest wavelength, which is violet, to the largest wavelength, which is red light. So it's violet, blue, green, yellow, orange, red, right? And so if we want to go into reverse, the visible spectrum is usually given by Roy G. Biv. So Roy, red, orange, yellow, green, blue, indigo, and violet. And so then as we move down, we've got infrared, we've got microwave, radio wave. So these guys have very, very large wavelengths, so very small frequencies. And they are not capable of doing anything to your biological molecules. They are not energetic enough to damage anything, right? So this is why we use them frequently in things like cell phones and then our various FM and TV frequencies. All right, so let's go ahead and do a question, right? So this is asking for the wavelength in nanometers of red light that is emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th. So this is going to go back to our relationship between wavelength and frequency. So frequency times wavelength, so nu times lambda, is equal to the speed of light. And so again, speed of light is a constant, 3.0 times 10 to the 8th meters per second. You'll have the frequency, right? They give you the frequency. You'll be solving for wavelength. This will be your unknown. And the only thing to note here is that the speed of light is given in terms of meters, right? But they want you to, I guess, denote this wavelength in terms of nanometers. Okay, so there's going to be a conversion step between meters and nanometers. Just as a reminder, 1 nanometer is equal to 10 to the minus 9th meters. So the nano is the minus 9th. But I'm going to go ahead, so this will be actually on the video assignment quiz, so go ahead and calculate this, and then hopefully you get the correct answer. Okay, so since we are still dealing with light, we're still dealing with waves, we're going to talk about a couple of other characteristic properties of light and waves. So one of these is something called interference, right? So if you have waves, right, and they are completely in phase with respect to one another, so if you have one wave and it's added to another wave that is completely in phase with respect to one another, what you get overall is one big giant wave. So this is what we call constructive interference. And again, they're essentially just summing together to make this big giant overarching wave. We can also see something called destructive interference. So this would be taking a wave and adding it to a wave that is completely out of phase with respect to what it is. So these are taking two waves that are out of phase. When you combine them, they essentially just destroy themselves, essentially. So this is what we would call destructive interference. It's adding together two waves that are completely out of phase, so they just cancel each other out. Okay, so another property of waves is something called diffraction, right? So if you have a wave and it comes up to a barrier, and the barrier has this tiny little opening in it that is comparable to the size of the wavelength that's essentially interacting with it, what you will see is something called diffraction, right? So what will happen is the light or the wave will move through that slit and it will spread out in an overall area on the other side of the slit. This is what we mean by diffraction. They essentially bend around the slit. On the other hand, if you were doing the same thing with something like particles, right? So if you're just throwing tiny little ping pong balls at a barrier with a tiny little slit, you wouldn't see diffraction, right? You would only see ping pong balls come through that slit and directly behind the slit itself, right? They wouldn't be shot out here or be shot out here. Again, you would only find them in the area directly behind the slit. That is not what happens with respect to waves. So waves will spread out, they will bend around the slit, and so you will get them all the way out here, all the way out here, if you're measuring this area behind the slit. Okay, so if we consider these two properties, so both diffraction as well as interference with respect to wave-like behavior, we're going to see kind of an interesting little feature with respect to waves. Okay, so this is what we call a double slit experiment or a two slit interference. So let's say you have a wave, right? Let's say it's light or whatever you want, whatever type of wave you want to deal with, and you shoot it at a barrier that has two tiny little openings in it, right? So two tiny little slits in it. What you're going to get on the other side is something called an interference pattern, okay? And so I'm going to try to explain what I mean by that, right? So we know that light, since it is a wave, is going to encounter our barrier, right? And as it moves through the slits, it's going to bend around it, and it's going to diffract on the other side, right? So we're going to get this diffraction through the slit. It's going to do the exact same thing with the other slit, right? So as light moves through the other slit, we're going to get this exact same type of diffraction pattern. What we're going to get on the other side, though, is this various interference pattern, where we're going to get periods of dark followed by periods of light, dark, light, etc. And that's going to be caused because these guys, these two lights coming through the slits, are essentially going to meet up with respect to one another, and where they meet up and they combine in a destructive manner, we're going to get this darkness, and when they meet up and combine in a constructive manner, we're going to get light, right? So as they come through, we're going to get overall this little interference pattern of light, dark, because, again, of their various abilities to constructively and destructively interfere with one another, okay? So this is a property of waves, right? And so light displays this property. So if our light source or our wave source is light here, then we'll get this interference pattern. But you could also just do waves like waves in a pond, right? And you could see the exact same thing. So again, this diffraction pattern that we see is a property of waves. All right, so sometimes I'm not super great at explaining things like that, right? So the whole idea behind an interference pattern of this light, dark, kind of intrigued me when I first encountered it. And so I posted a video in the folder with respect to this video assignment. It's this YouTube video that essentially goes through what this two-slit experiment is supposed to be showing you. So it talks about the original experiment, Young's double slit experiment, that essentially proved that light was a wave because it produced this interference pattern. So I would suggest, if you want more information, you should watch this video. So watch video. It's only like, I don't know, like 7 minutes long. It's kind of cute, it's fun, and it's just interesting. At least to me it is. So I would again suggest that you watch this video if you want an actual demonstration of light producing this interference pattern. So when quantum mechanics was being developed, the current kind of prevailing ideas behind light and matter were the fact that light behaved as a wave, right? We had just demonstrated that light was a wave, or at least Young's double slit experiment did, and that matter was made up and consistent of particles. Right, so if we wanted to understand how light behaved, we were going to treat it like a wave. And if we wanted to understand how matter behaved, we were going to treat it like it was a particle, which makes sense. We kind of think of things with respect to matter in a very particular way. All right, so there were some issues, though, with observations that had been made at the time and this overall idea behind light and matter and this wave-particle duality, okay? And so three of those experiments, or three of those little issues that were developed, are given here. So one of them was called blackbody radiation. This is essentially having to do with the emission of light from really hot objects. We're not going to talk about this one, but again, it's one of those types of things where it could not be explained by the prevailing ideas at the time. The second, which we are going to talk about, is something called the photoelectric effect. And then the third is the emission spectrum of various elements, right? And so again, this is another one that we're going to talk about. All of these three things could not be explained by the prevailing ideas that light behaved exclusively as a wave and matter behaved exclusively as a particle. So again, we're going to talk about both the photoelectric effect as well as emission spectrums and how we can hopefully understand those ideas. All right, so what is the photoelectric effect? Okay, so scientists had known for a while that if you were to take metal and you were to shine light on it, that metal would eject electrons. So this is what we actually refer to as the photoelectric effect, right? So classical wave theory, again, we're looking at light and we're imagining that it behaves exclusively as a wave. So classical wave theory contributed energy of waves to both frequency, right? So we had talked about that. We know that energy is related to frequency. And classical theory also contributed energy with respect to the amplitude, right? So we knew that energy was proportional to amplitude. So again, this is classical theory with respect to where the energy of waves comes from and therefore where the energy of lights come from, right? So again, with respect to classical wave theory, how frequency manifests itself with respect to light was, giving us different colors, right, of the electromagnetic spectrum, or different regions of the electromagnetic spectrum, whereas where amplitude manifests itself in terms of light was whether or not something was bright or dim. So dimness versus brightness. The brighter the light, so bright. So the brighter the light, the greater the amplitude. The dimmer the light, the less the amplitude of light, okay? All right, so what did this photoelectric effect type of experiment, what did it actually look like, right? So again, what we're doing here is we're taking metal, some sort of metal surface, whatever type of metal you want to look at, and we are shining light on it, right? And so due to that light and due to the energy that's present in that light, we are getting these electrons that eject from the metal surface. These guys are little electrons. We are measuring that as some sort of current, right? So we have some sort of voltage source and we're measuring the current that is produced by shining light, right? So we have some sort of nice little current meter, okay? So again, according to classical theory, the energy of light was due to the frequency and the energy of light was due to the amplitude. So the kind of idea, or the prevailing idea behind the photoelectric effect, was that if you were to take light and you were to shine very bright light, right, so very high amplitude light onto the metal, you're going to get current. Okay, that was kind of the current prevailing idea. Also, if you were to shine very high frequency light, because frequency also has something to do with energy, onto the metal, you were going to get ejected electrons, you were going to get current, right? So they thought, all right, so if we shine bright light, if we shine very high frequency light, we're going to get currents in both ways because, again, the energy of waves, the energy of light, comes from both the frequency as well as the amplitude. Okay, so what did these scientists actually find with respect to this photoelectric effect? All right, so again, we're shining light on metals and we're seeing ejection of electrons, okay? And so if we go down here, we can see what an actual experiment like this would look like. This rate of ejected electrons means how many electrons. We're essentially just looking at current, right? And this little flat line here is essentially 0 electrons ejected, okay? And so what they found was that it did not matter how bright or how dim the light was. They did not see any type of electrons ejected until they hit a certain frequency. And this is what they called the threshold frequency. Okay, once they hit that frequency, they got electron ejection, right? And what they saw was that at this point in time, the lower intensity or the dimmer the light just led to less electrons being ejected, whereas the higher intensity or brighter light just led to overall more electrons being ejected, right? So again, down here, it didn't matter whether or not it was bright or dim. You weren't going to see any ejected electrons. Once we hit our threshold frequency, though, we did see electron ejection. And here, we just got more if the light was brighter, okay? All right, so this really couldn't be explained in terms of the classical idea behind light being strictly a wave, right? And so Albert Einstein was actually the first to propose that maybe light had particle-like properties. So it's a wave, but maybe some parts of it have a little bit of a particle-like nature. And so he proposed that the energy of light did have this particle-like nature, that maybe it was delivered in little things or little packets of energy, and what he called these little packets of energy quanta or photons, okay? So the energy of light is, instead of just being some sort of wave type thing coming in, maybe it's delivered in these little types of packets. he proposed that the energy of these little photons, or these quanta, was directly proportional to the frequency of light and not to the amplitude, right? And so he derived this little expression that related energy of light, so energy of light to frequency, and the constant of proportionality here was something called Planck's constant. It's this very tiny number, 6.626 times 10 to the 34th, right? All right, so if we know the relationship between energy and frequency, then we can also derive a relationship between energy and wavelength, because again, frequency is equal to c over lambda. So if we plug that guy in, then we can also get this relationship that relates energy to wavelength, right? So remember, lambda is wavelength. Okay, so now that we have this idea that the energy of light is particle-like in nature, right? So it's related to frequency entirely and has nothing to do with amplitude. We can essentially kind of go back to this idea behind the photoelectric effect and what we're actually seeing in the results there, right? So in the photoelectric effect, what we were seeing, wrong one, so this was frequency, and we were seeing essentially ejected electrons, right? And so at frequencies that were below the threshold frequency, we didn't see any type of ejected electrons, right? So these little photons of light, which we can calculate their energy of now, did not have enough energy to actually eject the electron. Once we hit our little threshold frequency, that's when we started to see ejected electrons. And so the energy of the photon of light at this threshold frequency essentially gave the electron just enough energy to overcome its little its bonds and be ejected, right? And so we essentially call this the binding energy. And so one photon of light with that energy was enough energy to essentially break whatever type of bond it needed to get that electron out, right? As we move to frequencies higher than that binding energy, then what we were seeing was ejected electrons, but these guys with this energy, or this photon of energy, had more energy than what was needed for the binding energy. So all of that excess energy essentially went in the form of kinetic energy, right? So the electrons that were ejected at frequencies above the binding energy had more kinetic energy. So they were moving faster because again we're giving it more energy with respect to whatever photon we're using, right? So this excess energy becomes kinetic energy, and these guys essentially pop off a lot faster. All right, so let's go ahead and do some more questions. So for the first one, we've got a wavelength of light. So wavelength of light for this guy is equal to 337 nanometers. And I want you to calculate the energy that is contained in one photon of light at this wavelength. So remember that energy is equal to h nu. And we do also have a relationship between energy and wavelength, which is hc over lambda. Okay, the only thing I would remind you is to keep track of units. So right now, this guy is in nanometers, and c was in meters, so that's an important little thing to note. C was 10 to the 8th, 3 times 10 to the 8th meters per second, and then h was 6.626 times 10 to the minus 34th joule seconds. So you should be able to calculate the energy of light given that. And then in the second question, it gives you total energy of a pulse. So this total energy is 3.83 millijoules. So that's 10 to the minus 3 joules. And they want to know how many separate photons does this pulse of energy contain, right? So up here, you're going to be solving for the energy of one photon, and this should be a small number, right? And then what we're asking, that's one photon that gives you that much energy. What we're asking is how many photons are going to be in this amount of energy, right? So if we get a small, tiny little number for one photon, then how many photons will go into this? And that's going to give you essentially the overall number of photons, if that makes sense. Probably doesn't, but So 1, calculate the energy of 1 photon using the equation, and then 2, calculate how many photons 3.83 millijoules of energy contains. Okay, so then in the next question, we have light at 3 different wavelengths. So we have a wavelength of 325, 455, and 632 nanometers. And this is going to be shined, all 3 of these wavelengths are going to be shined on a metal surface, okay? We then observe 3 different observations for each wavelength, right? So we have observation A, observation B, and observation C, okay? And I want you to tell me which one of these observations correlates to the 455 nanometer wavelength of light, right? So in observation A, we don't see any photoelectrons. In observation B, we see photoelectrons, and they have a kinetic energy of 155 kilojoules per mole. And then observation C, we see photoelectrons with 51 kilojoules per mole of kinetic energy. Okay, so again, each of these observations matches up with one of these wavelengths, right? And I want you to tell me which one matches up to 455. Again, considering that energy of each wavelength is equal to hc over lambda. You don't necessarily need to calculate anything here, but just understand the relationship between energy and wavelength. And that should ideally help you in answering this question. Okay, so the photoelectric effect kind of brought into question the exclusive wave-like property of light, right? So we had assumed beforehand that light had wave-like properties, right? And so the whole idea behind the photoelectric effect is that it showed that light, while we can imagine that it is a wave, also has particle-like properties, right? So the particle-like properties of light come in with respect to the energy of light. We imagine the energy of light being like these little photons, these little packets of energy, okay? So light, while we do imagine it is a wave, also has particle-like properties. So that whole idea and the development of that idea through the photoelectric effect kind of brought into question whether or not matter, which we had assumed to be entirely particle-like, maybe also had wave-like properties as well, right? So we have this particle-wave duality for light. Maybe for matter, we'll see the exact same thing. So maybe matter, while we believe it to be particle-like, maybe it will also have wave-like properties, okay? And so one of the kind of, again, underlying questions that had yet to be explained with respect to matter was something called atomic spectroscopy. Okay, so this was one of these puzzling questions where we couldn't explain it at the time. We couldn't explain what we saw with respect to atomic spectroscopy just by considering the particle-like nature of matter. All right, so what is atomic spectroscopy? So certain atoms and certain molecules, when you excite them, give off very distinct colors of light, right? So we can see this in the form of fireworks, in the form of flame tests. I don't know if you guys actually got to do flame tests, but when you burn certain elements, certain metals, they give off very distinct colors. We also see this in the form of things like neon lights, right? So a neon light is essentially like an evacuated tube filled with neon that is being excited by electrical energy. And when we do that, it gives off this very distinct glow, and this comes in the form of kind of this yellow-orange glow, right? So this is very distinct for the element. Neon, when it is excited, gives off this specific color, right? So you can kind of utilize it to characterize whatever element that is present in the tube, right? We'll see the same thing for other elements. So mercury, whenever you excite it via electrical energy, gives off this nice blue color. Helium gives off this purple color, and hydrogen gives off this reddish color. So again, these emission spectrums, that's what we're referring to, the colors that they glow are characteristic of the element, right? And so hydrogen, regardless of where it was prepared, when you excite it via electrical energy, will always glow red. Same thing for helium, same thing for mercury. Okay, so that's not necessarily the problem, right? Them glowing these specific colors. But what becomes more of an issue with respect to the model that we had, the classical model of matter is what happens when you take these colors, and they're glowing colors, and you pass them through a prism, right, or what we call a spectroscope. So when you pass light through a prism, what prisms do is they break it up into their component wavelengths, right? So if you were to take complete white light, so just normal light, and pass it through a prism, you would get essentially all of the colors of the rainbow. That's what the prism is supposed to do. So when you do the same thing with these elements and the colors that they're glowing, you don't get what you would expect, which would be all the colors of the rainbow. Instead, what you get is a very discrete pattern that, again, is characteristic of the element. So, for example, if we were to take hydrogen and the light that hydrogen glows when it's being excited by electrical energy, and we were to pass that through a prism, we would get on the other side what is called the emission spectrum of hydrogen. And what we see here is these very sharp, discrete lines at very characteristic wavelengths, right? So with respect to the emission spectrum of hydrogen, in the visible region, we only see essentially 4 very distinct lines. So we get 4 lines, and these are at very specific wavelengths, okay? Now, with respect to this, if you were to take a different type of sample of hydrogen and do the exact same thing to it, you would get the exact same emission spectrum with, again, these very sharp lines at these exact same wavelengths. So this is a characteristic property of hydrogen, okay? Not only is it a characteristic of hydrogen, but it also depends. All right, so no. It's on the element, right? So, for example, helium has its own very specific emission spectrum, and it's different from every other element on the periodic table. Same thing for barium, same thing for all other elements. They all have their own very discrete emission spectrum, again, that are given by these sharp lines at very specific wavelengths, followed by these spaces where there is essentially no actual lines present, no light present, right? So you can compare these discrete spectrums to something like a continuous spectrum, which is what you would expect from white light. So just normal white light passed through the exact same prism, you get essentially all of the characteristic wavelengths, you get all of the rainbow, or all of the wavelengths of the rainbow. So this was an issue, right? Nobody could explain why this was exactly. So the first person to try to model the actual emission spectrum of hydrogen was someone named Johannes Rydberg, right? And so he developed a mathematical model that is called the Rydberg equation, where he tried to determine the various wavelengths, right? So this guy is, again, wavelengths of light for the hydrogen spectrum, given this constant, which is called the Rydberg constant, and then this difference of the square of integers, right? Or the 1 over the square, the inverse square of integers, okay? All right, so what does this exactly say? So again, he took the hydrogen spectrum, and what he could do is he could essentially determine the various wavelengths, right? Given that M here and N here had to be integer values. So this was the big kind of development with respect to the Rydberg equation, is that these various wavelengths could be described by the difference in the inverse square of integers. And again, these numbers had to be integer values. Okay, so the problem with this is great, well, it can explain these wavelengths, or it can, like, predict them, I guess, but it can't actually explain them, right? It doesn't give us any idea on why we only see these very specific wavelengths, okay? So again, it's a model, but it doesn't actually give us any type of idea or any type of theory behind why this is. Okay, so the first person to try to actually explain why you actually saw this with respect to these various emission spectrums was this guy named Niels Bohr, all right? And so he tried to explain the emission spectrums in the following way, right? So he imagined that an atom, or hydrogen, had a nucleus, right? And then what he thought was that electrons would essentially lie in these radiuses, in these very specific orbits that had a very defined radius away from the nucleus, right? So he imagined these electrons kind of like orbiting the nucleus, like planets orbit, right? But they could only be at very specific fixed distances away from the nucleus, right? So he had one energy level a certain radius away, and then he predicted another energy level a farther distance away. Okay, and so these radiuses that these electrons were orbiting were fixed, right? And he imagined these guys going out and going out. Okay, so another big assumption that he made is that electrons could only lie in these orbits, right? They couldn't be found in between orbits, right? They had to actually be in these orbits. And again, these orbits were given these various integer values. So this is where it kind of comes back in with respect to the Rydberg equation. Okay, so with respect to the Bohr model, again, he imagined that these electrons were essentially in these orbits, and these orbits were fixed distances from the nucleus, right? And these electrons can only be found in these orbits. Now, his big leap of intuition, or his big idea with respect to these emission spectrums, is that we were seeing light being emitted from these elements because we were seeing transitions between these various orbits, right? So, for example, if we had an electron and it was in a higher energy orbit or a radius that was farther from the nucleus, right, it would, when it fell to the lower radius, right, the smaller radius closer to the nucleus, it would essentially emit this difference in energy between the two levels as light, right? And so that energy difference between these various levels would be emitted as light, and that's why we're seeing these very sharp, distinct lines in our emission spectrum, because it was due to these very specific distances or very specific differences in energy between these various orbits, okay? And again, this difference could be described by our h nu, or again, our hc over lambda, right? So the energy difference between these various levels was giving rise to these very specific energy wavelengths, these very specific energy frequencies. Okay, so Bohr believed that all electrons naturally, as is, lie in what is called the ground state energy level. So this is going to be the lowest energy state, or the radius that is closest to the nucleus, right? So this is what we would call the ground state. So again, lowest energy state. And when these guys absorb energy, and this can be in the form of light, or this can be in the form of electrical energy, or thermal energy, etc., they would be promoted, these electrons would be promoted into a higher energy excited state, right? And so again, if they absorb light that had an energy that was equal to this distance, then they would be promoted into a higher energy state, and they can go even higher energy states up above it, right? So this is what is called, this movement from the ground state to the higher energy state, this is what is called absorption. So they absorb light. We could also see a transition from a higher energy state down to a lower energy state, and again we would see emission of a photon of light that had this energy difference. This is what is called emission. Okay, so if we go from the ground state to a higher energy state, this is absorption. If we go from a higher energy state to a ground state, this is emission. And we can actually calculate this difference in energy between these various states via this equation, right? So this is how you would calculate just the difference in energy between these various energy states for the hydrogen atom, right? So this is essentially a constant, this 2.8 or 2.18 times 10 to the minus 18th joules times 1 over NF. So this means this energy value for the final state of the electron, right? So this would be some sort of energy value 1, 2, 3, depending on where we were. So n equal 1 is the ground state, and as we keep raising up, this is what n is referring to, and then minus 1 over Ni squared. So this would be the initial state. Okay, so again, final state minus initial state, and it's just the square of those two. So once you can calculate this change in energy between these various states, then you can also calculate the frequency of energy required to essentially achieve that delta E, that change in energy, as well as the wavelength, right? So we have these two equations that relate energy to frequency and energy to wavelength. And again, this would be the frequency or wavelength of light that would lead to these either absorptions or would be given off by these various emissions. Alright, so again, if we have an electron that's in a lower energy state and we absorb light and promote it to a higher energy state, again, this was called absorption. Right, and so this means that NF is greater than NI, so this is this instance. Then we're going to have a positive delta E. Right, and so we can again solve for the frequency of light that would lead to that via our little H nu equation. If we have emission, which is falling down from a higher energy state to a lower energy state, so N final is less than N initial, then delta E is going to be a negative value, right? But because our wavelengths or our frequencies of photons can't be negative, then essentially we have to take the negative of that. This kind of goes back to the whole system versus surroundings thing, okay? So regardless if we see emission or absorption, we can still calculate the frequency of light as well as the wavelength of light that would lead to these various transitions, and we would just kind of ignore the negative values with respect to these guys. Okay, so what is the problem with the Bohr model, right? So this Bohr model is nucleus, and then we have these very specific fixed distances away from the nucleus that the electron can essentially be in. Okay, so number one, it only works for hydrogen. So the Bohr model of the atom can't explain anything other than hydrogen. It can't explain the emission spectrum of anything else. Number two, Bohr still thought that the electron was orbiting, right? He thought it was moving in this circular motion around the nucleus. The problem with that is with respect to circular motion in charged particles, right? So if we're moving in some sort of circular motion, then this negative charge particle, or this charged particle in general, essentially is constantly accelerating or constantly decelerating. And so because of that, this guy should be constantly giving off energy in the form of light. And long term, it doesn't have this infinite well of energy to essentially supply to this. It would slowly lose energy and spiral into the nucleus. So this was another problem. Bohr could not explain what he called this peculiar mechanical stability with respect to these orbits. So that was another problem and another thing that this actual Bohr model of the atom couldn't explain. Okay, so let's look at how we would actually go about trying to essentially determine one of these types of problems using the little equation that we were just given. So we have an atom of hydrogen, right? And we see that it makes a transition between the n equal to 3 energy state and the n equal to 1 energy state, right? So it's starting at 3 and it's going to 1. So we can imagine, we drew out like our little energy diagram here, that we have n equal 1, n equal 2, and then n equal 3. And right now we have our little electron. It's in the n equal to 3, and it's going to the n equal to 1, right? So what we're looking at is this difference in energy between these two states. Once we know that, we can plug it into our little equation, energy is equal to h nu, to figure out what the frequency of light is, or more importantly, energy is equal to hc over lambda, to figure out what the wavelength of light would be to essentially account for this transition, or to essentially be the wavelength of light that this transition is giving off. Because again, this energy difference is being given off in the form of some sort of photon of light. Alright, so to do this, we will need our little equation that we just derived. So this was a minus 2.18 times 10 to the minus 18th joules. And this is times 1 over n final. So this is n final was equal to 1. So this is 1 over 1 squared minus 1 over n initial. N initial was this guy, which is equal to 3. So 1 over 3 squared. Okay, so then all we have to do is calculate this. So this is going to be equal to minus 2.18 times 10 to the minus 18th joules times 1 minus 1/9. So 1 divided by 9, which gives us 0.889. So we multiply that in. That gives us a delta E equal to minus 1.94 times 10 to the minus 18th joules. Okay, so again, what we're doing here is we're emitting a photon of light. So the energy of that photon is essentially going to be the negative of this energy of transition. So this is what we have been calculating, this transition energy. So the energy of the photon is going to be a positive 1.94 times 10 to the minus 18th. And so now that we have that, we also know that this is equal to hc over lambda, where h is Planck's constant. This is 6.626 times 10 to the minus 34th joule times second. And then c is the speed of light, 3 times 10 to the 8th meters per second. So we can go ahead and plug those guys in. And solve for wavelength. Okay, so when we do that, we will end up getting a wavelength equal to 1.02 times 10 to the minus 7th meters. And so frequently with respect to these types of problems, we'll want to be dealing with nanometers, because again, nanometer, that's the range of visible light. And so if we converted this meter to nanometer, this would end up being 102 nanometers. Okay, so again, in this transition of going from this n equal to 3 excited state to this n equal to 1 ground state, we'll see this transition, and it will be accompanied by a photon of light that has a wavelength of 102 nanometers. Okay, so that is going to be it for this video assignment. So again, I would be familiar with all the questions that I asked within. So questions 6.1 through, I think, 6.4, as well as being able to calculate this energy or wavelength or frequency of these various transitions in the hydrogen atom, utilizing our little equation up here, as well as our relationship between energy and wavelength, which we use down here.